Hello everyone, thanks for attending my presentation today. My name is Sai Pentpati and I'm going to present my work on optimization for monolithic 3D ICs and its application to heterogeneous 3D ICs. This flow is called Pin3D flow. A quick overview of the presentation. I'm going to start with a brief introduction and talk about the Pin3D flow, show some results for homogeneous 3D optimization, and then finally show a heterogeneous 3D IC design done with Pin3D flow. Recently, Intel presented their Foveros technology, which is used to design a single processor in a 10nm node plus 22nm technology node. The high-performance 10nm die contains performance bottleneck blocks such as the cores, and the low-power 22nm die contains all the other periphery logic which doesn't need very high performance technology. The integration method used here is a 3D bonding with a face-to-face connections done using microbumps of 50 micron pitch. So this 50 micron pitch is quite large and it can only support a block level partitioning because this has a fewer number of die-to-die connections. This picture presented in their paper shows the block level partitioning of the processor, and on the bottom we have all the periphery logic which doesn't have any high performance paths. This is one of our motivations to enable such optimization for monolithic 3D IC design so that we can study more about heterogeneous integration in a monolithic 3D IC design and how much we can improve in such a case. So why monolithic 3D integration? With monolithic integration, we can achieve a much finer sub-micron 3D pitch and have a larger 3D bandwidth. This supports gate level partitioning, which can improve path timing within a block and not just between various blocks. Compact2D is a state-of-the-art optimization flow for 3D ICs. In this slide, we show a pseudo 3D stage where the design is done in a 2D footprint and then shrunk and split into two dies to a 3D footprint. The optimization done in the first die is not fully useful in the 3D area, and so a final 3D optimization stage is required. For optimization in 3D, the cells are projected back on a single die, as the 2D tools only support a single FEOL layer, so there are overlaps between the cells from both dies. These overlaps are removed by splitting each row into top and bottom die rows, each having half width. Let's call a 3D row a subset of rows. That form a smallest repeatable unit that can span the entire footprint just from flipping and moving the rows, translating the rows. For example, in the 2D stage, this single row, we can flip this row to create a flipped row and then translate it to create the next row, flip and translate to span the entire 2D footprint. In 3D, this 3D row, which has two rows for top and bottom die, can be flipped and translated similarly to span the entire 3D footprint. But the number of rows in this 3D row depends not on the number of tiers but on the height ratio of the top and bottom tiers. For example, in a heterogeneous 3D IC design where the top die and bottom die will have different heights, let's say the height ratio is m/n, then the 3D subset or the 3D row has a set of LCM of m and n number of rows. In the heterogeneous check considered later, this ratio is 350:187, which makes the 3D row to have 65,000 number of rows. And this means we need to have 65,000 different variations of each cell, which makes this row splitting useless for such a technology. In Pin3D, we avoid row splitting and the number of LEF variations are equal to the number of dies in the 3D design or the number of tiers in the 3D design and not the height of the rows in different tiers. We use this using transparent cells and die-by-die optimization that contains full 3D context. So what are transparent cells and die-by-die optimization? So for example, in a normal die-by-die split, each die is independent and unaware of the routing and cells from the other die. But in our case, we have the full 3D connectivity in the both top and bottom die stages. In the top die stage, which is the one that is being highlighted here, the bottom die cells are made transparent, which are shown in the light blue to the placement engine. So the placement engine doesn't see them as overlaps to the cells, or it doesn't see any utilization from these transparent cells. So the placement engine effectively sees them as transparent and only top die cells are present at this stage. but the pins are left unaffected and the routing is still present and the timing information and path information is not changed at all. So the placement and optimization in this top die stage can be done with the full 3D context, full 3D timing and 3D congestion and every other 3D metric. So this is what we call the availability of a 3D context. Similarly, in the bottom die stage, the top die cells are made transparent. This is what we mean by a transparent cells and 3D context. So what is the use of this and how are we going to use this? Pin3D optimization takes text structure and timing information, library timing information as inputs along with the pseudo 3D design. The flow of operations is legalization, routing, time enclosure, and an optional ECO stage to fix any persistent timing violations. As discussed before, during legalization, the 3D context drives the placement in each tier. So this is done with a timing driven legalization so that we can easily so that it can easily be useful for time enclosure later on. We also do a manual 3D congestion driven legalization. So what this is we define a soft spacing rules between the top die cells so that whenever possible the tool tries to space the top die cells and leave some space in between them. Why is this useful? Because whenever an MIV is routed from a top die to a bottom die or bottom die to a top die, the MIV needs to pass through the white space where the top die cells are not present. So if the top die cells are crowded in a huge region like the normal non-congestion driven routing that is being shown here, the cells are placed very close to each other and MIVs cannot be placed in large groups of cells in a large group of area. So an MIV that needs to connect to a cell in this huge cluster needs to pass through a white space that is much further away. So we use this congestion driven legalization so that there are lots of spacing between the cells and MIVs can easily access the cells over the circuit. So this is the timing and congestion driven legalization followed by routing. So routing can be done at any stage and it's not a die by die stage because at any stage we have the full metal stack and nothing is modified in the metal stack. So the wires can be modified for in the top and bottom FUL at any stage. So routing can be done in a single pass. Optimization is also similarly done in a die by die fashion as we talked for placement. So coming to the ECO. ECO is never shown before in a 3D IC design. So to show the possibility and the applicability of ECO using our Pin3D flow, we use a simple register sizing algorithm that finds the paths with negative slack and appropriately downsizes or upsizes the registers to move the slack closer to 0. So this allowed us to improve the number of timing violations from 449 to 270 timing violations in the design, and the total native slack decreased by 35% or 34% without any increase in the total power or even the increase in total sequential cell area. The layouts show a 2D and 3D optimized designs. The black areas show where we see an absence of routing, and cell is where the memory macros are occupied. And the next, the memory macros are especially well optimized in 3D design because we split the memories onto 2 dies and the memories don't need to travel over a long area. So we see the macros connecting to the memory are almost half or even shorter than half of the 2D wires. So that's one of the main improvement when we go to 3D. So let's look at the full chip PPA results. The PPA results here are normalized with respect to 2D for both C2D and Pin3D, and the C2D design is independently routed and doesn't have 3D optimization stage. And one of the reasons is that we don't have the 3D optimizer with us to look at its impact. So this only shows the impact of Pin3D optimization over C2D without any optimization, and also Pin3D optimization with respect to a 2D optimization. So what's happening with respect to 2D design? The Pin3D design has almost 26% smaller wire length, and with respect to the C2D design, we have a 9% smaller wire length because of a timing or congestion driven placement that helps during the routing stage. The MIV count, on the other hand, we see that the Pin3D uses almost twice the number of MIVs, and one of the reason is that Pin3D does not only use MIVs for connecting cells from bottom to top dies, but whenever there is a timing critical path, for example, let's say this net is a timing critical net with a huge native slag, and there is a lot of congestion that's happening on the top die. So what can Pin3D do is that instead of using the top die, it uses this bottom die metal layers where the topmost layer is almost free, is very free of congestion. So instead of routing through here, it uses one MIV to connect here, and then the wire can go through here and use another MIV to connect to the cell. So we have two MIVs on a net where it can only be routed with one MIV using a independent die-by-die routing. That is the reason we have almost 2 times the number of MIVs. For some MIV, for some nets, we have more MIVs, and even for some 2D nets like this, it can also be not for this, but for this, it can also be it can also have MIVs by going down to the bottom die and coming back up in case in case the tool deems it necessary to reduce congestion or improve the timing. So as we said before, the memory nets are especially well optimized in 3D, and so we see that the output latency of the nets compared to 2D is almost like 40% reduced. So this is a root mean square average. So it slightly leans toward the high output latencies, or ways the high output latencies more higher. And also the switching power is almost like 16% reduced, and it's mostly because of the again the wire length reduction. And the total switching power, if you see, is also like 14% reduced. This is again from the wire length reduction, but internal power is not reduced very much because internal power depends on the cell area, and cell area depends not only on the wires but also on the cell cap or the input capacitance of the cells. The overall timing in power shows that Pin3D has 8% smaller power, and the worst timing or the effective frequency is slightly better in Pin3D, as seen from the increase in the effective frequency compared to 2D. The effective frequency is not very much improved because the target frequency is the same. So 3D design or the optimization engine doesn't want to simply over optimize the design. The total native lag is worse than 2D, and this is because of the clock network in 3D design, and which we are going to see here. So when we compare 100 register to register critical paths in the different designs, 2D, C2D, and Pin3D, and all the numbers here are also normalized with respect to 2D clock period, which is the same for all the designs. So we see that the Pin3D average path lag for the register to register group is much worse than 2D. But we see that this is not simply because the paths or the cells are not properly optimized, because the path delay is actually like 9% smaller in Pin3D, but the native lag is coming from the slightly worse clock skew optimization for the register to register critical paths. Since we see that the clock skew in these register to register critical paths is the average clock skew is like 140 picosecond higher, which is one of the main reasons for this worse paths lag in the register to register group. But this group doesn't dictate the target frequency, and so the target doesn't dictate the effective frequency, and so the effective frequency is actually still slightly higher than 2D. So Netcard is an open source RTL. So previously we used an industry RTL. That's why we have to normalize all our PPA values. Whereas Netcard is an open source RTL, and we use it to show the absolute PPA numbers. It doesn't have SRAMs, so it's a much simpler design, but it still follows the similar trends as we discussed before regarding the wire length, MIV usage, switching power reduction, etc. Due to this being a simpler design, the total native lag is well optimized here, and the 100 critical path average shows that the clock skew is not as worse as we previously saw in the industry design, and the average path lag is also very similar. This is because the design is much simpler and clock skew is much better optimized in this. So that's why there still needs some more analysis or more work that needs to be done in terms of 3D clock design in the complex designs like we shown. Let us now shift our focus to implementation and optimization of heterogeneous 3D IC. For heterogeneous 3D IC, we use a simple AES design which has 100,000 cells, and the bottom die uses 9-gate 45 nanometer and the top die uses 9-gate 15 nanometer. The placement and routing layers shown here are the final 3D place and route results. So let's see the flow that we use to create these layouts. Pin3D still needs a pseudo 3D design, and no 2D tools support heterogeneous synthesis or place and route. So we had to use a single PDK for pseudo 3D. Here we chose 15 nanometer just to test the timing optimization when some cells are later connected to 45 nanometer. So using the 15 nanometer PDK, we designed our pseudo 3D stage, and once the stage is done, the tech inputs are created such that the bottom die LEFs and LIBs use the 45 nanometer data, and the top die LEFs and LIBs use the 15 nanometer data. The routing structure is created by merging the top die and the bottom die, like the 45 nanometer and 15 nanometer LEFs together with a custom MIV layer to act as an intermediate between them. One requirement here is that each cell in 15 nanometer should have its equivalent in 45 nanometer, and there should be a 1:1 pin mapping between these equivalent cells, so that we can push one cell to the other cell of one die to the other die without any loss of pin connections. The following table shows the output of heterogeneous Pin3D optimization and its impact. The partitioning is done to achieve area balance, as we show here. The ratio of the area split is 0.958:1, so it's pretty well balanced in terms of area. And because of the area balance, we need to have a lot more cells in the top die compared to bottom die, because the 15 nanometer cells are much smaller. So the cell split is 2.25:1, but the total power split is 5.43:1, because the 15 nanometer cells are have high power consumption. And what's the use of this high power consumption? These cells run much faster. If we look at the timing results, before doing any 3D optimization, just from splitting the 15 nanometer pseudo 3D design into two dies and then changing one of the die to a 45 nanometer die, we see that timing becomes much worse. Like for the target frequency of target clock speed of 500 picosecond, the worst native lag is 615 picosecond, and total native lag is 280 picosecond, 80 nanosecond. But once we do the 3D optimization, and once the Pin3D adds buffer on both the dies, like we see here, the timing goes back to a much reasonable 50 picosecond worst lag and 1.4 nanosecond total slack. If you look at the critical path, if in this heterogeneous design, it has 18 cells in total, and the total path delay is 553 picoseconds. And of these 18 cells, 7 cells are on the 15 nanometer die and 11 cells are on the 45 nanometer die, and these 11 cells consume 500 picosecond of the delay, whereas these 7 high power consuming 15 nanometer cells only consume 50 picosecond of the delay. The clock tree network is completely on the 15 nanometer die to avoid any variations in the clock, and we see that's what we are saying here, where the wire length is on clock wire length is on the top die, and all the clock buffers are on the top die. So we are able to optimize heterogeneous 3D IC design using our Pin3D flow. As a quick recap, we have seen how Pin3D performs 3D timing closure, routing, and legalization. We also see that Pin3D gives us much better timing benefit compared to 2D design, and also power benefit. We saw that how the Pin3D can be used to optimize a heterogeneous 3D design. This applicability to heterogeneous 3D ICs is exciting and useful, as heterogeneous 3D ICs can try to alleviate some of the thermal issues and also try to improve the power benefit of 3D ICs and expand the circuit design horizon even more. Thank you.